4 different sites, the beams are brought together and they collide. And when they collide every 10 nanoseconds. So that's 100 million collisions per second. Each collision produces one of those pictures I showed you. And the pictures are now collected with these enormous detectors. So this is the Atlas detector. What you see here, this is a man here. You can see in the center. Give you some idea of the scale. These big things here are toroidal magnets, which are used to bend the particles that come out of a collision, so you can measure their velocities and masses. The heart of the detector is here. Many different layers of different simulators and calorimeters, and it's extraordinarily complex. Tens of millions of cables, 2,000 physicists working with this collaboration, and it took 15 years or so from the beginning to when it began to run. It will run for another 20 years. It's a totally massive undertaking, comparable to the pyramid. But better than the pyramid. The pyramid is just a tool of some arrow. Here, I was discovering the secrets of nature. Now, let me tell you about the first success of the LHC, which started 5 years ago. This is one of the first events, in the picture here. The particles are coming together, you'll see, and boom, there's a collision, one of the first collisions. And experimental colleagues take these billions and billions of events and sift through them to find something new. Now, to find something new, you have to understand the old stuff very well. You have to understand the background, because you're looking for one event in a billion. You have to understand that a billion events are well understood in order to take out the new event. And 3 years ago, a little over 3 years ago, the first success was the discovery of a particle that was predicted by this extra part of the standard theory, the Higgs vector. And it's just a little bump. So the green swath is what you expect from theory plus other many experiments that have been done. And what was observed was a little excess of events centered around, could be interpreted as producing new kind of article, which is what we would expect to do. Now, that was a great discovery, and the theorists who had predicted this mechanism and this particle 50 years ago, not the Nobel Prize the year after that, 50 years after their theory. 2 weeks ago, the LHC groups, after running at twice the energy, increased the velocity, announced their first results for 2015, and they also see a little bump. Both groups, 2 experiments, see a bump at the same place. Not something that was particularly expected, and at the moment we don't know whether it's real or a fluctuation. We don't know what it is, or whether it supports which of the many, many ideas that have come up in the last 40 years it supports. One of the most interesting ideas is supersymmetry, which I'm not sure I have an explanation of in this version of the talk. So let me just say that if this what might be a discovery is confirmed, it might be the first indications for what we call for a radical extension of the way we think about space and time. In effect, it would be the discovery of quantum dimensions of space and time. But I don't have time to explain it. But up here, we can't do experiments. We have to rely on theoretical speculation of the type that Einstein was very successful in his early years and very unsuccessful in his later years. And that's a dangerous thing, but one that we pursue. The biggest clue is the fact that gravity is involved. Because our understanding of gravity so far has been classical, without the strange nuances of quantum mechanics. Quantum mechanics and gravity have been a theoretical challenge since Einstein's theory. Quantum mechanics in the early 20th century united them. And the direction that has been pursued now for 40 years at least is string theory. The idea that if you look at a quartz very carefully with a better and better microscope, you don't discover that it's made out of subquartz and so on. You discover that the quartz is actually not a point-like particle, but an extended, vibrating string. And the remarkable, this general framework that we're still constructing, not yet a theory, although it's called a theory, string theory, but we're still on the road to formulating understanding that theory. One way of looking at it is to say that all particles are really vibrations of a string-like particle. A string can vibrate in many different ways. That's why a violin doesn't just play one note, it plays many overtones, many notes, infinite number of notes. Same reason string can vibrate in many ways. And the remarkable thing is that one has this framework in which the unification of all the forces we've observed, including gravity, follows naturally. So that's a direction we've been pursuing. And in pursuing that direction, many new ideas got developed, including, again, thoughts about the most basic concept of our understanding of the physical universe, space and time. Early string theory suggested that space-time has extra dimensions, that each point here, this point right here, this point, is not a point. It actually, if one were to look at this point with a very good microscope, you would see that it's a curled up, higher dimensional, six-dimensional manifold, which looks maybe something like this. And it turns out that such construction that have 6 extra spatial dimensions curled up into beautiful manifolds whose properties are determined by equations which are generalizations of Einstein's equations, explain why many of the features of the standard model that otherwise we have to take for granted, like the fact that there are these 3 forces and the fact that there are 3 families of quarks and leptons and the masses of the quarks and leptons, all might be explainable by the geometry of these magnified extra dimensions. But from the more fundamental level, we're now at a point where we're being forced in developing these ideas to ask questions that challenge our basic assumptions about space and time. And we're in a sense asking today and trying to understand using all the theoretical tools we have, what is space-time made of? Space and time, remember, is not something you observe. It's part of your theory of the universe, which each one of you discovered as a little infant before you could crawl. You started to crawl around on the floor to reach a toy. You had to figure out how to move, and you constructed a model of the universe, the world, where events and things exist in space and move as time goes on. We don't directly measure or observe space-time. It's part of our theoretical framework. And like many other parts of our theoretical framework, over the years physics has had to modify because of relativity, quantum mechanics, and now the quantum nature of space and time. So let me end with just for the young people in the audience. I've often asked for advice. And how can you become a good scientist? How can I win a Nobel Prize? Question. And my 3 bits of advice are pander and stoke your curiosity. Curiosity can easily be killed by television, the internet, or bad teachers. But it is the driving force for science, and it's the reason, one of the reasons that society supports the kind of science that I do, because no immediate application. The other requisite is passion. You have to be passionate about what it is you do if you want to succeed. You should choose a career or a subject matter or a line of research that you really enjoy and are passionate about, because that is the fuel that fuels discovery. But it also takes perseverance. Nothing comes easy to anybody. It requires hard work. But if you're curious, it's worth persevering. If you're passionate, it's worth it. And enjoy doing what you're doing. You can enjoy the hard work. Or to put it another way, these 3 lessons are: follow your heart, passion and curiosity. Aim high and take the chance of failing. If you don't aim high and try to tackle the most difficult problem, you'll never succeed. If you aim high and fail, which there's a good chance of, happens all the time, happens to me. No matter, if you follow your heart and enjoy what you're doing, you'll have a great time along the way. Thank you.
Thank you, sir, for that wonderful presentation. We now have the question and answer session. We request the moderator to present the questions to Dr. Gross.
Good morning, ladies and gentlemen. In the run-up to this important event, we have been collecting questions over the internet over the last 2 or 3 days, and it's been The Alumni Association, American Alumni Association, has been quite instrumental in getting the web interface ready, and after an elaborate process of voting, we have shortlisted a few questions, and though the list is quite big, I think we'll have to restrict the amount of time available, for the questions and answers. We also have picked up some questions from the local audience, so together we have a fairly comprehensive list. I'll start with the first question, and it sort of steals words from your presentation. May I assure you that these questions were collected a few days back. Do you agree with the statement, math is the language of the universe?
Yes. Galileo was the person who first enunciated that statement. And mathematics is the language of science. And it's obvious that we use mathematics all the time in every branch of. But the remarkable thing that has emerged from Galileo's time, over the last 400 years, especially in fundamental physics, which is the most developed of all sciences and the most quantitative, is that the more we get to the heart of understanding nature, the deeper we get, the more unified we get, the math becomes more abstract, more beautiful, more powerful. In fact, today at the frontiers of knowledge, which I hinted at, where we ask what is the nature of space-time, we seem to require new mathematical structures that mathematicians themselves are exploring. And indeed, mathematicians and string theorists work together in what might be called mathematical physics or physical mathematics. So the answer is certainly yes, and I think that this actually reflects I don't have time to go into detail, but a deep feature of physical reality. Mathematics is, in my view, not a human creation. It too is a reflection of physical reality.
The next question, how would you attract students to theoretical physics?
Well, like I tried to do now, by showing them how exciting it is. But there are other good reasons. First of all, I could easily give a sales pitch for theoretical physics. First, physics. Physics is the heart of science. Everything is physics. Chemistry is the understanding of atoms, which are, of course, physics, and biology is, of course, the understanding of molecules, which are made out of atoms. Everything in the end, in the reductionist sense, is based on our understanding of the basic physical processes.
Okay. Now, this is somewhat of a bomb.
So, but the other thing is that, so therefore, if you get a good education in physics, you can do anything. And there are many examples of people with a physics education who then move into biology and are very successful, or into finance, or anything. Physicists, in effect, can do anything. That's not necessarily true of biologists. They can't do physics, for example. So it's a very excellent education based on 400 years of incredible progress in our knowledge of the physical universe.
Here's a big one. Could you please describe science in one word?
Well, it's roughly what I said, trying to understand nature, the observable world, but you can try to understand something in different ways. Homo sapiens, about a few hundred years ago, so a very short amount of time, discovered a new method, which isn't based on some kind of written word or oral tradition or philosophical postulates, but rather three important ingredients: observation, quantitative measurement, and constructing mathematical models and theories and testing them by observation or by measurement. That scientific method has developed and improved over 400 years. And roughly, to some extent, I might define science